Welcome back to Module 6, the completely randomized block design. So this lecture continues where we left off, where we had looked at advantages and disadvantages of the randomized complete block design. We looked at the ANOVA table, and we had looked at details related to making a field layout. So in this lecture, we're going to continue with some of the mathematical calculations that are underpin the ANOVA table, and we will have the opportunity to do those yourselves during the recitation. Then we will look at the linear additive model for the randomized complete block design. We'll look at some aspects of programming in both SAS and R, and then a couple of calculations, some scenarios where you can try it yourselves. So this is the, just to remind us where we had got up data from table 10.5 in our text. This shows both the layout and the data for a randomized complete block design with 3 replications for each of 4 treatments. You should recall then that the replications are randomized, the randomization is restricted such that all of the 4 treatments occur within this first block. Likewise, the 4 treatments are re-randomized in the second block, denoted block 2, and finally a third randomization for the third block. These data are the data that we'll use for calculations for this particular example. You can follow this, these calculations also in the text. I believe it is table 10.2, page 135. So just a refresher here, some points to note: the random allocation of every treatment within each block. Typically, we would orient the plots to maximize field variation between the blocks and minimize variation within the blocks. We want that variability to be incorporated into the block effect, not into the experimental error. Just another point to note here that the blocks could be arranged in groups. Most commonly, we use rows or columns to orientate that are orientated perpendicular to the expected source of variation. But as you might see in one of the examples of the videos, where in a greenhouse there is variation in both directions, and so in that case the blocks might be groups. So often rows, but generally whatever is the best arrangement that aggregates the or minimizes the variation within those blocks. Typically, this randomized complete block design is relatively intolerant of missing plots. The CRD is very tolerant of missing plots, particularly because we have the requirement that the blocks are equally represented, or the treatments are equally represented within the blocks. And if we had, say, one block we had a bias compared to the other blocks and the treatment was not represented in there, then that effect would be omitted for that particular treatment. We'll talk more about this next week. So we're going to go into the calculations, and there are a couple of ways of doing this, but we'll follow the format that's used in the textbook, and these calculations are shown in table 10.5. Just for explanation here, we will be calculating the treatment effect, the block effect, we'll be fitting the overall model and then using that to calculate the residual error. The next slide shows a possible layout in Excel that duplicates those calculations that are laid out in table 10.5. So we calculate the treatment effect then as the treatment mean minus the grand mean. And the cumulative total for all of the treatment effects will be 0 since we are defining each treatment with respect to the mean for the whole experiment. So there'll be some treatments are over the mean, some treatments fall below the mean, but because they're defined in terms of the mean, the net total of those will be 0. Likewise, it's a little not as easy to conceptualize perhaps, but the block effect is also defined relative to the grand mean. So some blocks will be higher than the overall experimental mean, some blocks will fall below the overall experimental mean, but the net effect will be 0 since they are defined in terms of relative to the experiment grand mean. So then we can calculate the model. Sometimes this is termed the predicted or the fitted values. And we would calculate the model as the grand mean plus the treatment effect plus the block effect. That is to say, it's the mean of the experiment plus the deviation from the mean due to that particular treatment calculated by the treatment effect, plus the deviation from the grand mean due to whichever block it's located, that value is located in, and that's calculated from the block effect. Mathematically, this can be calculated as the treatment mean plus the block mean minus the grand mean. Computationally, these two options are the same. Finally, we will calculate the residual error, which is the individual value itself, the Yij value, the yield in this case for the ith treatment in the jth block, minus the modeled value. So this then defines the difference between the actual observation and the modeled value. Of course, we will accumulate the squared residual values, will give us the residual sum of squares, as we will see in this very next slide. So here's a possible layout. This is a simple screen capture. I ran this in Excel, so you should identify this format here. But just to show equations might be accomplished. So I can go through this somewhat quickly because you will be duplicating this Excel table, and in doing that during the recitation, you should get a much better sense of how these values were calculated and maybe have some intuition on what these values mean. So in the column then we can define the varieties, A, B, C, or D, the block that they are assigned to, the data, the observations that is taken from table 10.5. The grand mean then, of course, is the same for all of these values. This is the experimental mean. The treatment mean then is the mean of these three values. The 7.6 is the mean of these, the 9.8, 6.8, 6.2. Likewise, the treatment mean for C, 6.6, the treatment mean for D, 8.3. The block mean is a little trickier because this value of 8.5 is the mean of the values for block 1, a mean of 7.4, 9.8, 7.3, 9.5. Similarly, the mean for block 2, 6.85, for block 3 has a lower overall mean, 6.4. So these are repeated for the blocks respective blocks within treatment B, likewise the respective blocks within C, and respective blocks within D. This is our raw data we can go ahead and calculate. We can calculate the individual yield minus the grand mean defines the overall variability of the experiment. We would square those individual values, and we would calculate then 18.81 as the total sum of squares. Moving on to the next effect in a model, the treatment effect. We subtract the treatment mean from the grand mean. We get these individual deviations. We would square those, and so the sum of the squared treatment deviations, 6.63, we would term the treatment sum of squares. Likewise for the blocks, then the block sum of squares. We can see here that the cumulative total for the block deviations is 0. Cumulative total for the treatment deviations likewise is 0. So to calculate the model then, we can calculate, do this computationally as the grand mean plus the treatment mean minus the grand mean. That is the treatment effect, plus the block mean minus the grand mean is the block effect. So here we can see the model statement that defines the calculations for this experimental design, the grand mean plus the treatment effect plus the block effect. We can calculate these modeled values. The residuals then is the difference between the actual observed values and the modeled values. These are the residuals. Of course, these total to 0. And we square those. The squared sum of the deviations then we term the residual sum of squares. If you are quick with a calculator, you could total up the 2.4, the 9.78, and the 6.63, and these would sum to the 18.81. Thus, we have partitioned the total variation in the experiment. The total sums of squares has been partitioned